Okay, cool. So today we're going to well, last time what we did is we described gradient descent in other norms. For example, gradient descent in the LP norm, where P is larger than 2. This generalized gradient descent in the L2 norm that we said were, what is it? Smooth in that norm. Okay, so today our goal is to see a pretty simple example of that in action. And I'll try to, well, at least going to be some like parameters and stuff, but I'm going to try to explain settings where they come up, so you might have to see a little more motivation for it. Okay. So in this, so today the main problem we're going to be considering is the problem of approximate L infinity regression. Okay. And this problem is to try to find a y. So I'm going to write it this way. Find y such that ay minus b L infinity norm is at most 1 plus epsilon a min over x ax minus b infinity norm. Okay. So here just A is a, let's say, M by N matrix, and B is an M dimensional vector. And just for clarity, I guess here it would be R, X is N dimensional, and here I guess Y is also N dimensional. So this is the problem that we're going to study. And the goal is to get an iteration count depending on something like, well, an iteration count depending something like, well, I'm gonna write big O here, but this is like sketchy, of like 1 over something like epsilon squared is what we're gonna get today. Okay. The point is that this is a low accuracy thing. The iteration count depends on polynomially in epsilon to get an epsilon approximate solution. This big O is kind of a lie. Also, we're going to have some, it's also going to depend on like some logarithmic factors, and also some, the more importantly, it's going to depend on some properties of the matrix A. That's more important. It's going to depend on some kind of like how well A approximates the L infinity norm. Let me write that, like how well A approximates the L infinity norm. Now, yes.
The way that we set up the transformation.
Yes.
So in this case, if AX equals B has an exact solution, then that has to also find the exact solution.
Correct. I think that's how I want to set it up, let's say. Yeah.
Is there a reason why we switched like the views a little bit?
Okay, fine. Let me be a plus epsilon here. I'm just gonna be lazy. So what I want here, this is a multiplicative approximation. And let's say you just add an epsilon, so we don't care too much about the exact case, just to be a little precise. Yeah. I don't want to worry too much about the case where like AX equals B has a actual solution. So I'm going to allow for this extra plus epsilon, let's say. Okay. Good. Yeah, good question. So yeah, once again, the iteration count, I want it to depend polynomially on epsilon. So this is like kind of a low accuracy type of algorithm. And there's going to be some dependence also in this big O on like properties of A. Now, whatever I'm presenting today was initially developed to some extent in the context for fast graph algorithms for the maximum flow problem, where in that case, by using properties of graphs and some graph theory, they were able to set up an L infinity regression problem where the matrix A actually had like some nice parameters. and then they got a good runtime out of this. So that's vaguely the context. And well, that's at least a context in which some of these assumptions I'm going to make on A approximating the L infinity norm are reasonable. Okay, good. So before getting into anything, does anyone have any suggestion or thoughts on how one would even get started on trying to design such an algorithm? Maybe motivated by the discussion in the last lecture of gradient descent with respect to other norms.
It seems that our step size depend, like, kind of was determined, like, kind of was related to like the dual norm, like at every location, but I don't know what the dual norm, the infinity norm.
Okay, so I'm just going to start taking some notes over here, which these are all, that's definitely a good point.
Had like this general thing where we're like, oh yeah, here's like the step size that you're expected to take if your function is L smooth. So we might want to kind of think about whether our function is smooth at all.
Yeah, so
Or at least suppose that.
sure, these are good points. So the first point that was said is that in the last lecture, when we were discussing gradient descent with respect to some norm, it was important to identify what the dual norm is. The dual norm of L infinity is the L1 norm. So that's just dual norm of L infinity is L1. So that's a good thing to note. And also the other thing that's probably worth that's worth remembering is that the step size and the iteration count depended on the smoothness on the iteration count depended on the smoothness of the function. Smoothness of function in whatever norm we want to measure in the norm. So it'd be good to understand, how you prove that such functions are smooth or something like that.
So the function in this case is you plug in x and then you evaluate like ax minus b in the norm.
Yeah, so for example, the function may refer to fx. Well, like the natural thing is for the function to refer to this example, right? Okay, good. Yes. Okay, good. Could you, so the suggestion was to like take a different LP norm for a large P and try to run something. What's your motivation for doing that? Why is L infinity, like working with L infinity itself, not good? Okay. Okay, yeah, good. So let me just state that point again. So remember that in the last lecture, what we had argued is that the LP norm is something like O of P smooth. Its smoothness is dependent on P, right? So in our case, we're working with L infinity regression. So like in our case, we're working with L infinity regression. So if we were to naively try to set P equals infinity and do some kind of smooth gradient descent, then we run into some trouble immediately because the function, first of all, is not smooth. Maybe even put a different way, it's like this, the L infinity, like ax minus b infinity norm is not actually a differentiable function. Yeah, it's a math, it's not differentiable. So that already causes a lot of issues, right? So these are all good things to know. And that motivates that when you're working with something like an L infinity norm, if you don't want like super high approximations, what you can do is you can instead work with an LP norm for a very large P, and while not really affecting this approximation too much. Okay, so that's a concrete lemma that I'm going to try to describe. So does anyone have any? Okay, let me just write the lemma first, and then anyone could ask questions about what the point of this lemma is, or any context. So here is the lemma. For P equals, I'm gonna say log n over delta, let's say. I'm trying to decide what log, okay, let's say that log is base e, okay? It holds that I think ax minus b p norm, at least ax minus b infinity norm, and most 1 plus, well, I'm just going to write like 3 delta here. The 3 probably doesn't really matter. Ax minus b infinity norm. Okay? So this is, well, actually, sorry. Let me not write ax minus b. Let me just write like, for any z, this is just true. This should probably be an m and z. 1 plus 3 delta is fine. Z infinity, where z is in r to the m. Okay, cool. So that's a lemma. Does anyone have any questions about the context of why such a statement is useful in the context of trying to get approximate L infinity regression? So it, probably just to say it, the reason that such a statement is useful in the context of approximate L infinity regression, a little more concrete, is that first of all, instead of minimizing the L infinity norm of this, we're going to instead minimize the LP norm, right? That function now is differentiable, it's smooth, so we can try to use the techniques from the previous lecture to like approach the problem of minimizing it, right? So those are good things. The other thing is that if we had set delta to be something like epsilon over 10, then P is something like log M over epsilon, right? While the new objective we are trying to analyze, the LP norm, is within a 1 plus epsilon factor of the L infinity norm, because our goal was just to get a 1 plus epsilon approximation in the first place anyways. So let me just write this here. So one would apply this. One would apply this lemma for something like delta equals epsilon over 6, let's say. And then this would reduce the problem reduce the problem over there to instead trying to do a y minus b p norm at most, something like 1 plus epsilon over 2 a x min over x ax minus b p norm. I'm not going to write the plus epsilon because I'm being a bit lazy. Yeah. Good. Okay. Does someone want to see the proof of this? It's not terribly okay, maybe everyone think for a bit on how you would try to prove this, and then I will try to present a proof. And the hint is that it's not actually very challenging, but you should try to, yeah, maybe think about it for a little bit. probably also need delta as the most one, maybe. Something like that, I think. Probably. Okay. I'll just add that. So while I didn't give anyone that much time to think about this, hopefully you at least got a feeling for the type of proof methods one might try here. So let me try to actually prove this now. Okay, so for notation, let's let M equal the L infinity norm of Z. And let's say that the ith coordinate of Z equals M, right? We know such an I exists by the L infinity norm. So now notice that the P norm of Z to the P is the sum of I from 1 to M, Zi to the P, which is at least M to the P. So this establishes the lower bound, right? So this establishes the lower bound. Now for the upper bound for this side, Z, P, and most of that, you just write that Z P norm to the P is at most sum I equals 1 to M, Zi to the pth power, which is at most M times capital M to the P, because each of these terms is at most M, and there's M of them, right? So Z in the LP norm is at most M to the 1 over P times M. So now it suffices to upper bound what this M to the 1 over P is. So it suffices to upper bound what this M to the 1 over P is. And now M to the 1 over P is M to the delta over log M, which is E to the delta, which is at most 1 plus 3 delta for delta and most 1, as I had described, right? Okay, so that completes the proof. That's it. This is just some generic approximation of the LP by L. Cool. Did anyone have any questions about any of this? Cool. Okay.
The negative delta or something? Minus.
No, that's not how things work. It's M to the delta over log M equals M to the 1 over log M to the power delta. This is E.
No.
Okay. Okay, so that's like most of that's the setup basically. So now we're going to discuss how to actually solve LP norm regression approximately using the tools that we discussed last. And there's going to be a few runtime dependence. Yeah. Well, let me erase this. I think we remember the problem. So now our new goal is to find y in R to the n such that ay minus b in the LP norm is in most 1 plus epsilon min over x, a x minus b in the P norm. That's our, and we're going to make an assumption on the matrix A. And here's the assumption on A. The assumption on A that we're going to make is some kind of approximation with respect to the element that for all x in R to the n, it holds that ax L infinity, I guess, is at most m times, ooh, well, I used the letter m over there. Well, I guess we'll just use it again. Mu times x L infinity. Okay. That's going to be the assumption we make on the matrix A, is that A is some kind of a good approximation to the L infinity norm. So, the reason that like you kind of need this kind of assumption, at least for what I'm doing, if A is like kind of wildly long in some direction, then yeah, anyway.
It's just maximum absolute value, sum of absolute values on a single row. The upper bound.
The upper bound, yes.
The lower bound.
It's not clear. Yeah. Yeah. You have to be a little careful with the lower bound, but yeah. It's not super clear. Yeah. Generally, the lower bound is the one that's like a little bit weirder to establish or something. Yeah. But in some applications, like people have been able to construct matrices that satisfy this property and then use this framework. If A is invertible, but yeah, sometimes A is not invertible, but this sort of thing can still hold. That's right. No. Now, the main thing to prove is that, well, we have this function, right? We want to prove that this function is smooth. And we want the smoothness probably to depend something on, well, you want the smoothness to depend on these parameters of A. So let me just write this here. Next goal again. We want to instantiate the framework from last time. So we want to bound the smoothness in the LP norm of the function ax minus b in the LP norm. Let's do actually squared because that's what we were dealing with last time. Here's the next lemma. So the lemma, the function f of x equals ax minus b p norm squared for p equals like O of log n over epsilon, as described over there, is O of, I think, probably m squared p smooth, I think is correct. M squared p smooth. Where does this quantity m squared come from? Well, it comes from two main places. The p is from the smoothness of the function x p norm squared from last lecture. And the extra m squared comes from this extra distortion on when like of ax versus x in the infinity norm. So that's where this m squared comes from. Let me write down the proof of this so that, well, let me just write down the proof of this so we're on the same page. For simplicity, let's define the function hz is z p norm squared. And we know that h is O of p smooth. And recall what O of p smooth meant. What this means is that it's equivalent to for all v and z in R to the m, that v transpose Hessian of h at z, v is at most, well, I guess it would be, I think last we got 2p minus 1 times the LP norm of v squared. This is from last lecture, the calculation that was done at the end. So now given this, we want to argue that the function f is smooth, right? To do that, let's first compute the Hessian of f. The Hessian of f at x by calculus is A transpose the Hessian of h at ax minus v times a. Okay. And thus, for some v transpose Hessian f of x v equals v transpose a transpose Hessian x minus b a v, which is at most, by using was smooth from the last lecture, a v p norm squared, right? Now, remember for our choice of p, by using this lemma here, that this quantity is at most some constant like 4a v infinity norm squared, and most 4m, sorry, I lost a factor of 2p minus 1 here. 2p minus 1 times that. For the choice of p, this is the most 8 times p minus 1 times infinity norm squared, and most 8p minus 1 m squared x infinity squared. And by applying, this is the most 8p minus 1 x p norm squared, right? God, I lost another m. M squared x p norm squared. So the conclusion is that this function is 8p minus 1 m squared x p norm squared. Let me pause for a bit on this so that everyone has a chance to digest what's going on and ask any questions. Did anyone have any questions? Any kind of question about this calculation here, or kind of what the intuition motivation for any of this was? Sure.
We can just combine like our things from last time and everything yourself. Essentially what's happening.
Yeah, so yeah, good. So the question is like kind of what's the point of this? So all that's going on here is that um okay, maybe let me put it in two steps or something. So all that's really going on here is you're saying that um I'm combining the chain rule and the fact that the p norm is smooth to get some smoothness bound um that's in terms of p, well p from last time, and how much a can affect the LP norm, right? Like a little more directly, you could have just said this is 2p minus 1 times a vp norm squared, which is at most 2p minus 1 times like however much larger a can make the LP norm itself times vp norm squared. And then the use of this lemma was actually just to relate the p norm and the infinity norm a few more times, which is why he lost a couple more constant factors here. So that's the motivation, or like this kind of the point of here. When I take a linear transformation, then smoothness is kind of maintained as long as the thing I'm transforming by kind of respects the norm that I'm operating in. That's really all that's happening. Yeah. Good. Now that we have that this function is O of P smooth, we can directly invoke the theorem from the last lecture to, yes, is that a question?
The assumption on A, all the assumptions, like the entire assumption, if you replace the infinity norm with the p norm, you get the same thing, right?
That's correct. The question was, this assumption that was written down was in terms of the L infinity norm. We could have just written it down for the LP norm. That's right. And it's the same here or something like that. Yeah. So if this was the P norm, it would be an identical assumption as long as P is like, as we've chosen today, being like logarithmic in size. Yes. Good. Now, given this, we know the function is smooth. We can just directly use the theorem from the last lecture in iteration count bound. However, this bound actually is going to be not the best, and I'm going to describe how to better analyze the process to get a better iteration bound. I'm going to erase this. Hopefully everyone remembers. So now, given the function f of x is x, given the function f of x is ax minus b p norm squared. From now on, even though we're trying to approximately minimize the p norm over there, I'm just going to write p norm squared. This only affects the approximation by like a little bit, so it doesn't really matter. It's multiplicative, right? Where it's this, let x star be the minimizer of f. Right. And now, as in the setup that we've gone over so many times, we initially have some point x0 in r to the n, right? Now, so here is the naive analysis. If you run gradient descent in the LP norm, if you run gradient descent in the LP norm, I'm not going to write out the exact iteration. Then, and your points are, let's say, x0, x1, all the way to x capital T, right? Then for the parameters r equals max over y such that fy and most fx0 y minus x star p norm then f of xt minus f of x star is at most what? O of, it was L r squared over t, right? Which is O of p m squared. That was the smoothness parameter from here is p m squared times r squared over t, right? So if we had defined opt to be the actual true optimum of function value f of x star, we need to set, I guess, let me call it opt squared. Then we would need to set t to be O of, well, sorry, let me just do it this way. I'm going to let opt squared be f of x star. The reason for doing this is so that opt is just the min over x, ax minus b p norm. Then if we want epsilon error, we would need for p m squared r squared over t to be at most epsilon opt squared. So this implies a choice of t to be p m squared r squared squared. Okay. Definitely there's an epsilon somewhere. Epsilon in the denominator, right? Okay, let me just describe whatever is going on the board here one more time. All I'm working through here is if you were to take the gradient descent theorem from last time on gradient descent for LP norms and use what we've developed so far and just directly invoke the theorem, then what iteration bound do we get for getting an epsilon approximate solution? That's all that's being analyzed here. Okay? Now, to do this, remember that we had this important parameter r, which was the maximum over y such that the function value is at most f of x0 of the distance to x star. This is the radius parameter r, right? We have the smoothness parameter, which matters, which is pm squared by, the board over there. So in t iterations, the error is pm squared r squared over t, right? If we let opt be the value we're looking for, then we want to have error epsilon opt squared on the function because it's the square function. By putting it all together, you get t to be p m squared r squared over epsilon opt squared as the number of iterations.
So this is like seems to be a better dependence on epsilon than we were promised.
No, it's not. Okay, good.
It's in R, hidden in R.
It's hard hidden in p. P is log m over epsilon. P is log m over epsilon, so it's actually hidden in p, interestingly.
So like actually one thing that I'm also wondering about, so you said that only in the L2 norm we're guaranteed to like constantly move towards like X star.
Yeah.
So do we have a bound on R? Could we get really far?
So the question is like here R is not just the original distance, it's some other thing which is like the max of function value of most f of x of y minus x star p norm. And the question was, can you give some bound on that quantity in terms of something? And the answer is we will get to that or something like that. Yeah, it's a good question. Okay, so what I wanted to say about this bound is that this bound is possibly really terrible because imagine I started very far away from x star, then this R parameter is huge. Opt is like probably much smaller or something like that. I mean like this guarantee on A gives you some kind of normalization already. That's kind of the point of the thing over there.
That's why we need it.
Yeah. But R could be much, much larger than opt even in that case, because I could just start super far away from, X star, and then this ratio is huge. Yeah. So this dependence actually is possibly really terrible if R versus opt is really huge. So maybe let me take a bit and ask if there's any suggestions for how one would improve this dependence by kind of applying some tricks. Got a go. Yeah.
Okay.
Sorry.
So like,
Sure.
I think like at least one copy of the epsilon is within like the factor of p. So what if we don't approximate them with like p norm altogether, but using like another class of?
Okay. This is sorry. So actually, the 1 over epsilon squared is like not bad. Like that's actually what you expect in some sense. The bad part is the R squared over opt squared. That's actually the part that's like possibly sketchy because this is saying if I somehow initialize very far away, then my dependence is immediately horrible or something like that. So the part that at least I feel is more critical to fix is the R squared over opt squared. Fixing the epsilon is also an interesting question, but only, well, let's say after that part gets fixed. That makes sense. So yes.
But what if we have like an initial guess,
Mhm.
and then once we reach that number of concepts, then we update the guess?
Yeah. So okay. Very interesting suggestion. The suggestion was you initially have some guess, right? Or like you have some guess of opt, or you have some guess of the initial point, and then you go for a while, and then it's kind of like instead of using the theorem to get all the way to opt in one shot, you kind of use the theorem a little bit to improve your distance, and then after improving your distance, then you kind of use the theorem again. And maybe in that way, this R squared over opt squared isn't, doing so badly anymore. So that's the general idea. Let's see if we can make it work. Okay. So once again, the idea is kind of like, don't use the theorem in one shot. Use the theorem just to make some progress. And then after that, then you update your value of R because your function value is like, not going to go up anymore after that. And then use it again, et cetera, et cetera. So yeah, let me describe some way to try to do that and see how it goes.
Algorithmically, nothing changes.
Correct. Algorithmically, actually nothing, purely in the analysis. Yes. Algorithmically, we're still just running the same gradient descent thing, nothing changed. It's just that in the analysis, we're going to look at it a little differently, kind of analyze it in phases. Analysis in phases. Good. Okay. Good. So I'm going to let the parameter kind of k be so k is going to like represent, k is a parameter that will represent a phase. Represent a phase of the analysis. And a phase starts when f of, I'm gonna write xt, is at most 2k, and it ends when like f of x of t prime is at most k. So the phase is when my value hits 2k, and then I do some steps, and then the value eventually is less than k, and then the phase ends. Okay. And the final phase, wait, actually, let me put squareds here again. I'm going to try to get the normalization right. So I'm going to go from k squared to okay, let me just do k to k. That's better. K to k, no k squared. And the final phase is when, let's say, f of xt is at most, let's say, 4 times opt squared. This is when the function value is already within a large constant factor of our desired minimizer opt squared. That's the final phase. And now we're going to try to analyze how many steps each phase takes to complete. So so now let's analyze the phases. Analyze each phase. Now let's start with the phases before the last. Phases before final, right? Start with the phases before the final phase. Now let's analyze all the parameters for this phase, right? Basically, we can still use this bound, but within that phase, if that makes sense. Okay. Good. So by this analysis, in t steps, the error, or like f of x, okay, let me change the, let me say in t prime steps, f of x of t plus t prime minus f of x star is at most O of p m squared r squared over t, where here r is, again, the maximum distance of y to x star in the p norm over f of y at most f of the initial point, right? F of where we initially started, we call it xt, which is at most 2k by the definition of the start of the phase, right? So once again, all this is saying, like all I've written here so far is mostly just simple things. This is saying by using the theorem, we know that in capital T prime steps, that my error is at most p times m squared times r squared over capital over t prime, I guess, where r is the maximum of the distance from y to x star over f of y at most 2k. And why can we assume it's 2k? It's because we assume that at the start of the phase that the function value was already 2k. So that's why we're assuming that it's at most 2k. Okay. Now, obviously, the main part of the analysis will be to bound a capital R. And so let's do that now. Where do I want to do that? Namespace. This is probably. I'll do it here, I guess. We don't need this anymore. I don't know where this move is. Yeah. Now let's bound R. To bound R, what do we say? Okay, yeah. So to bound R, notice that because f of x is, well, f of y is ay minus b squared and most k, and f of x star is a x star minus b p norm and most k. By the triangle inequality, on norms, ay minus ax star, these should be twos here, P norm is at most AY minus B P norm plus AX star minus B P norm is at most something like 4 square root K, right? Now, yeah, like this is just the triangle inequality because the P is a norm. And now by the condition on A, the lower bound condition, we know that this is at least mu y minus x star P norm, right? Yeah, good. So we conclude that y minus x star P norm is at most 4 root K over mu. 4 root K over mu. So the parameter R is at most 4 root K over mu.
Why is like f of x star less than 2k?
Remember f of x star is the optimizer of the function, right?
Yeah.
And f of y is like the current value we're considering.
Yeah.
So the final the optimal value should be at most just 2k. It's at most the original value, right? Yeah. Like actually the optimum. The optimum is at most any other value, right? So that's why it's at most 2k. And this one was by assumption. Now we're almost done with analyzing everything.
This is where we needed the lower bound on the L infinity one.
That's right. Yes. This is the only place lower bound gets used. Yeah.
Okay. So if we were okay with r squared over squared.
Yeah. Yeah. This is the place the lower bound gets used. Yeah. Okay. So now we had this bound p m squared r squared over t prime. So you went p m squared r squared over t prime. So, okay. So like when does the phase end? The phase ends when this error is at most something like k over 2 or something. So the phase ends when the error f of x like t plus t prime minus f of x is at most something like k over 2. Like because the phase ends whenever the function value falls to under k, right? So as long as the error, like the final error is at most something like k over 2, then the phase it had ended. So when is this at most k over 2? For the choice of r here, that's p m squared 16k over mu squared and most k over 2. Okay. T prime. So you can pick t prime to be something like O of p m squared over mu squared. Okay. Yeah. So the conclusion here is that each phase before the last one takes O of p m squared over mu squared, which is, just to write it out, O of log m over epsilon m squared over mu squared iterations. Now the number of such phases, well, notice that within a phase, the function value error halves, right? So the number of phases that it takes is only logarithmic in the initial error, which in general in this course, I'm just going to accept as like fine. Like I'm just going to assume the original error is not like larger than logarithmic. So then the total over these phases is kind of O of log m over epsilon m squared over mu squared times log of the original error, like f of x 0 divided by opt, because that's the number of phases it takes to get from the original function error down to the last phase. Now I'm just going to write out what the final phase bound is, because it's really nearly identical to what we just described up here, except there's an extra factor of epsilon because we're looking for an epsilon approximate error. Here we were okay with just some constant approximation error because we just wanted to move on to the next phase. But in the final phase, there's nothing to do anymore. So you need to actually pay the epsilon finally. So in those phases, the final phase would be p m squared over epsilon mu squared, which is log m capital M squared over epsilon squared mu squared. So summing these together, that's the total number of iterations for running this algorithm. So notice a couple things. The first thing is that there's some dependence on m squared over mu squared, which is how well A approximates the LP norm. There's a 1 over epsilon squared dependence, which is, well, that's the dependence versus the accuracy, and there's an extra logarithmic factor because we needed to set P to be logarithmic. Okay. Okay. Did anyone have any questions about this analysis that happened here and kind of, yeah, and whatever was proven throughout the course of this lecture? While you think on that, I will try to write an informal, at least, well, I'll try to write some theorem statement here, possibly a little bit informal, but slightly informal. Running LP gradient descent produces a point y.
Right, f of x in phase m, is it f of x star? Supposed to be in the top one.
Correct. Infinity. In something like O of log m log something like something. Before I talk about the theorem, which is really just to recap what happened, did anyone have any other questions about the analysis? Sure. Maybe let's start with your call. Let's
Okay. Is there, you could do this phase analysis always if you could have some kind of bound on R in the phases, right? Like that's, like before when we did
Correct.
demonstrating something, we could still do this analysis. And it would give you an improvement if you can bound R in the phases.
That is correct. The question. Okay, so the question was, if you were able to bound R better, you can continue the phase analysis even in the last phase. That is correct.
No, you asked, I think you asked whether you could do this for the stuff we've seen in prior lectures, and if you'd get
Like other norms and stuff too, you could also do that, right?
Correct. Yes. I don't believe it helps. I think, yeah, you should think about whether it helps below the final phase, but I think in this case it does not. In other cases, it can though, I believe.
Asking about like, if you did this for the L2 norm, would you get something?
Oh, for the L2 norm, would you
I
get
think the
something?
reason is that you don't, is that you have a linear.
You
dependence
probably
on-
save, ooh,
Save 100.
you have to be a little careful. I mean, if you look at L2 regression, you have exactly the same setup. I think the issue is in L2 regression, you just get a high accuracy thing because it's Richardson. Or not Richardson, it's like, yeah, you get something high accuracy out of it.
Final phase, I just mean like doing the phase analysis before the final phase, like you can do that part for gradient descent for other norms, right?
Sure, yeah.
But would you get something out of it? Like, would we get like an improved like Richardson if we
Mm,
analyzed it?
I think the issue is that to make the phase analysis work, you needed some property of the matrix A. So
Which we didn't have, like, didn't we
I
have
mean-
some sort of smoothness kind of?
but remember, Richardson was already getting high accuracy dependencies. Like Richardson was already getting like log 1 over epsilon type things, and these are all 1 over epsilon squared. So like
Yeah,
it is
I
indeed
think
better.
It's not intuitive, at least to me, that like, you wouldn't expect to get even better. Like, I think it sounds like it's intuitive to you that that's like the best you can ever hope for.
It's worth thinking about.
Yes, so I mean, my question.
Mhm.
So I guess like what happens here is that we're using this property of the matrix to say, okay, if like f of y is not that far from f of x star, then y and x must be relatively close together
Correct.
because of these bounds. And then what are we doing here? Like, I feel like I'm kind of losing it. So like,
All that's happening here is we are taking the iteration bound and we're plugging in the value of R we got there. That's all that's happening.
okay, so like, are we accumulating the number? So essentially, we're accumulating the number of steps to get from k to k over 2
And then
to divide like the
so
power.
yes, so k to k over 2, it turns out the number of steps does not depend on k because you get a cancellation because of the bound on R.
Okay, so it's different, and then you do, it's logarithmic.
And then you go k over 2 to k over 4, and that's another step. And then this is a logarithmic number of steps. Okay. And then the final phase is when you already get to somewhat close, and then that one you pay an extra epsilon because you just like.
So why?
Because there, like you're going, you should check this, but there you're going from error opt to error opt epsilon times opt. Yeah. Somehow the value of R doesn't actually get any better once you get too close. The value of R is only gets better when you're already far away. It doesn't get better when you get too close. Something to think about. I don't want to super formally do it here. So in the last maybe 5 to 10 minutes. Okay, maybe let me first just state what we proved today, and then I will take a small aside. Okay, so the slightly informal thing we proved today was that if you run LP gradient descent for P is something like log M over epsilon, starting at a point x0, you produce a point y that gives a 1 plus epsilon multiplicative approximation to the L infinity regression problem. And the number of iterations depends something on m squared over mu squared, where m and mu are the properties of the matrix A, up to some logarithmic factors and some epsilons. And that's the number of iterations to produce such a bound. Okay. So yeah, now I'm going to kind of just briefly discuss some alternate, well, like an alternate setup for the L infinity regression problem. So today I kind of set it up via this smoothness of LP norms. There is an alternate setup people sometimes use, which is this function called the softmax function that I feel it would be improper if I didn't mention it. So let me write down, so let me at least write down what this softmax function is, and go from there. So going all the way back to what we started with today, our initial goal was L infinity regression, which is we wanted to analyze this quantity, right? Instead of doing this, we reduced to analyzing this quantity for P, which was log M over epsilon. There is an alternate approach that is sometimes used based on something called the softmax function. And let me write out the softmax function. It's actually very, well, it's very much the same spirit in some sense.
I mean, the P norm for large P and the softmax are close. And I guess this is
Yeah.
evidenced by the fact like triangle equality of most the infinity norm, right?
Yeah. So the softmax function is just an alternate approximation of the L infinity norm, basically. And let me just write out what it is. Okay. So let me just do it with the function h of x is x infinity instead of this ax minus b, because we don't really care about it anymore. It's really not so important. So I'm going to define the function h sub lambda of x to be, what is it? 1 over lambda log sum I equals 1 to n at e to the power lambda xi plus e to the negative lambda xi. So this is called the soft max function, and it satisfies, well, I guess exercise. You can check the following. You can check that h lambda of x is at least h of x, and it's at most h of x plus probably log 2n over lambda or something. Yeah. 1 over lambda log 2n. So now, basically, so now if I wanted like delta additive error, what you can do is you can set lambda to be just, log 2n over delta. So once again, instead of trying to for example, if I'm given an L infinity regression problem, instead of solving the L infinity regression problem directly, what I could instead do is take this soft max function for a well-chosen value of lambda that would kind of depend on the amount of error that I'm okay with tolerating, and then just minimize the softmax function. Well, obviously to do this, you need to know that the softmax function is smooth. Turns out that it also is smooth. Okay. So I guess once again, another exercise. The function h lambda of x is O of lambda smooth, this time in the L infinity norm itself. And thus, you can, another natural algorithm, a natural algorithm is running L infinity gradient descent on, well, basically some like soft max version of ax minus b infinity norm. Doing this, let's just say that the analysis is almost identical. Yeah. Analysis really is just almost identical. Like the phases even kind of go the same way. I think the only change is that you have to like adjust the value of lambda over time or something to make everything work out. But yeah.
So I'm used to seeing softmax. It's probably the same, but I just want to ask, I guess. So it's like as like sum of e lambda xi over like the normalization.
Oh, do you put
the
the log on the inside? Like, are you putting 1 over 2n on the inside?
Actually, I don't know. Never mind.
I guess okay. It's possible that what you've seen softmax as, which might be the more standard one, to be honest, I actually don't know. Maybe the version you've seen has that.
No, but I don't know. If I remember.
Okay.
Yeah. Sorry.
1 over 2n on the inside, and that's just whether like this goes here or like here. Sometimes people average on the inside or the outside. I don't remember. Yeah. But yeah. So the softmax, once again, it's a different kind of good approximation, and it also is smooth. So no, these things are all good. Cool. Okay. Okay. So yeah, that's all I had. Feel free to ask any more questions if anyone has anything, and probably starting next time we'll switch away from these low accuracy algorithms and go back to high accuracy algorithms in a slightly different regime. So, yeah. Yes, question. Mhm.
Like, um, like, how these results are and also like where have you seen these communities since?
Yeah, that's a good question. I wish I had a better answer, but the place I learned it from is a paper on trying to solve the approximate maximum flow problem. Sherman or like the concurrent one. Either yeah. So there's a paper by Jonah Sherman in 2013 on approximate maximum flow. And there's another paper by Kellner, Lee, Orecchia, Sidford in 2014. These papers basically they have the same set of results. They really have very similar sets of results. Sherman's it's a little shorter, a little more compact. This one's probably written with a little more detail. But those papers use the softmax function to do it. And I think it's kind of known in general that you could instead take a p-norm approach, and that's very similar. But these papers use the softmax approach, and they give an algorithm that is exactly using L infinity gradient descent to solve this maximum flow problem. And in that setting, they're able to design a matrix A using the graph structure of the max flow problem that has these like L infinity lower and upper sandwiching bounds. Yeah. And then they basically do the analysis as I described here today.
Yeah, so another tricky norm that people like me often care to work with is the Hamming norm. Are there like tricks to do this kind of thing on the Hamming norm?
That's not a continuous thing, right?
Hamming norm?
Yeah.